Thank you for that talk, and thanks for all of the questions. The next talk is going to be about faster cross-platform builds by Fabian, Ara, Greg, and Tiago. This works. Forward.
Hopefully, this will be a nice complement to the last talk. If the last talk is speaking about Bazel's ability to integrate builds with different kinds of platforms and all different kinds of ways, and the state of that and how well that works and how well that doesn't work, this talk is focused on some inefficiencies in the performance of this model and things that we're trying to do to maybe address that and help that a little bit. So obviously, Bazel users are fairly, I think, enthusiastically trying to do builds, Bazel builds in all kinds of different multi-platform environments of all different variations. But they have noticed some surprising inefficiencies when they try and do these builds, that they don't always operate as quickly as they hope they would. There have been different, I think, specific reports and sort of kinds of complaints about things that are going not working as expected when doing their builds. But I think the general sort of binding pattern across all these complaints is trying to do the same sort of build, mixing platforms, either the platform that you're running the builds on, or the platforms that you're targeting the builds for, that you're trying to build your apps for. And especially trying to do that with technologies or languages that are ostensibly platform independent, where this sort of thing shouldn't really matter for those languages. Like Java is a very prominent example in Android. So I think what users reasonably expect when they're building, say, platform-independent languages across multiple platforms is that you should be able to mix and match platforms, and you shouldn't have to do extra work for those languages because, again, they're platform-independent. None of this should matter. In practice, it does matter, and users do see that build work is redone when it doesn't seem like it should have to be redone, and that causes, I think, fair complaints and dissatisfaction. Why do Bazel users even care about any of this in the first place? I think probably one of the most common scenarios that I've seen looking around on GitHub is development shops where the developers are working on MacBooks. I think this is being referenced a little bit in the last talk as well. And they like to have a system where they could run cheaper CI systems using cheaper Linux machines, run the CI systems, and then developers can come into the workday at the beginning of the day and get the benefits of that CI having run and being able to basically get cached results when they start running on their Macs. And that doesn't always work as expected. But probably more fundamentally is, we're ultimately talking about waste. We're talking about build actions that are running more often than they conceptually need to, which ultimately translates to slower builds, more resource utilization. And if you're an organization that's paying for your compute costs in some way, then more money that you have to spend. Again, for no real good reason, because we're talking about scenarios and kinds of build actions where this sort of thing shouldn't be necessary. So why is all this a problem in the first place? Why doesn't this stuff just work already? If you're building Java, why should any of this matter? Java, the whole promise of this and similar languages is none of this sort of thing should matter in the first place. So why does this matter? Okay, so it all comes down to caching, I guess. Like many things in Bazel and build, there's a lot going on in this slide here, but I guess the gist of it is Bazel fairly reasonably tries to cache as much build work as possible to try and not redo build work when it doesn't have to. And it probably, I think this is a pretty complete diagram of what's going on across the build system here. But I guess the key things I might point out on this slide are just that this happens both within a single user's workstation. So if the same user does the same build 2 times in a row, they don't have to redo work that they'd already done before. And of course, it also happens across multiple users and across multiple workstations when organizations have some sort of remote setup with a remote cache or remote executor system. And that's, of course, the basis of trying to be able to efficiently do builds and scale builds across large projects. So in order to do that, in order to cache effectively, you have to know if two actions are the same. I think a fairly intuitive way to think about whether two build actions are the same or not is essentially, maybe a slight simplification, but essentially, if you see an action and you've seen that same command line with that same inputs, then that's the same action that you've run before. Or if you've seen that you run that same action with the same command line, the same inputs, you have that in a cache somewhere, then you can just return that value from the cache instead of having to rerun that action again. I think that's a pretty intuitive sort of definition of whether or not you're seeing the same action or not when you're looking to see if you have a cache hit. And I think it works fairly well, and it's essentially the model that Bazel applies and powers caching. And it works reasonably well, but it does run into a little bit of trouble when we're mixing platforms. So you can already see on the slide here, probably most prominently, even if you're just looking at what the command line of the action is by itself, in practice, that command line includes platform-specific information in it for various reasons that this talk will get more into as we go into it. But because of that basic fact, right, changing the platforms will pretty much automatically change the command line that you're actually running for an action, which is starting to create problems for that simple model of whether an action is cache shareable or not. So in this slide here, right, we have two examples of two actions which should be able to share the same cache hit. It's the same exact action. It's running some hypothetical Java compilation, both being run on Macs using some shared remote cache or remote executor system. And in this case, all the machinery is exactly the same, and everything should and would, in fact, be able to properly share caches. So in this example over here, you only need to run one of the actions and get the outcome of running both of them. But if you switch that out, going back to this common CI scenario, where if one of the machines is now a Linux machine running some CI or whatever, doing whatever it's doing, it's a Linux machine and not a Mac machine, then what happens in practice is you're staging, you're still running the same Java compilation, but now you're doing it with different Java compilers, because even though Java is platform independent, that doesn't mean that the Java compiler, which runs on the host machine, is platform independent. It's not. The Linux version of this is going to be running a Linux version of the Java compiler, and the Mac version is running a Mac version of the Java compiler. And what ends up happening is that information is reflected in the paths, and the command lines are different, and we don't get a cache hit, and we can't share the results. Even worse than that, we could conceptually clean that up and just try and name those compilers, put them in the same path so they look like they're the same, even if they're different binaries, but and make the path look the same. But that doesn't change the fact that they actually are different binaries with different digests. So even if the command line was the same, the actual inputs to these actions are legitimately different. They are not the same action in a trivial way. We know that it's ultimately the same thing. It's intended to be the same thing. It's intended to be the same output. But from a simplistic view of whether actions are the same, if you're not aware of the special properties of how the Java compiler works, these are actually legitimately different actions, and these results can no longer be shared. And this is pretty direct reason why the CI issue that a lot of people have experienced happens, when why people can't share the work of their Linux CI systems when they're running builds on their MacBooks. So this issue, Tiago has been looking into and has been working on some feature work to try and address this when the host platform that you're running the builds on varies, even though the outcome is ultimately the same. And he's worked on a feature called cache key scrubbing, which he's going to get into later in this talk. And that's intended to improve this and address this sort of dilemma and make the caching logic a little bit more intelligent in this regard. And then there's another variation where even if you are using the same host machines, even if you have two different builds, both running on a Mac or whatever, the same machine, even if you're targeting different types of architectures. So one of the builds is building an app for a Mac, and the other one is building an app for a Linux machine, and they have different architectures that they're targeting. Again, it shouldn't matter to the extent that we're compiling something like Java files. It shouldn't matter. We should still be able to share the results, but we still have the same problem that while the inputs to the actions won't be different in this case, because in this hypothetical example, both of them would be using the Mac version of the Java compiler, the command lines still are different because Bazel, for reasons, embeds information about the platforms that you're targeting into the paths of the outputs. And that's highlighted in the slide over here. I won't get into the reasons myself. Ara will get into this a little bit more when she goes more into what we're trying to do about this. But there are reasons for that. And it then creates these same complications where as things stand now, these two actions cannot share the same cache hit. Running on the same machine, running platform-independent logic, but targeting different platforms, can't share the same work because of the way that Bazel constructs the paths in the outputs. I also might add really quickly, and I think our other speakers will get a little bit more into this. This also applies not just to platform information. It also applies to build rules that use transitions. So if transitions are something that you pay attention to and that you find interesting or like, but sometimes find frustrating with some of their performance implications, this also speaks to that issue as well. So we have an experimental feature that Fabian, Ara, and I have collaborated on, which we call path mapping, which is attempting to address this side of the problem. So I think that's all I have to say. I'm just basically introducing all of this here, and I'm going to pass this on now to Ara, who's going to go into more detail about path mapping and how that's supposed to work and hopefully help the situation.
Thank you, Greg, for the overview of our problem space. Hey, everyone. My name is Ara. It's actually my first time here speaking at BazelCon. Super happy to be here, and it's a pleasure to meet everyone. So I'm going to talk about path mapping. Let's first, for context, let's first understand where does Bazel store the build outputs and why. So the number one criteria is safety. So when we decide where we store the build outputs, the criteria is safety. That means we cannot allow two actions that produce different output to write to the same path. And if we do that, it will create a race conditions. So for example, if we have an ARM compilation of mylib and an X compilation of mylib that produces a different output, and we allow them to write in the same input, the same output path here. And then later on, the ARM link of my binary needs this specific output. So which one does it get? So this whole situation right here is called action conflicts. And in Bazel, we do have checks to for this scenario and fail the build with such conflicting actions. So to remedy this, we add the CPU information into the output path to distinguish the different outputs. But doing so could harm the remote action cache because the path here is directly related to how action caching works. So the remote action cache is a map that maintains a map that has the action digest as a cache key, and the action result metadata is a cache, the value. And the action digest is a hash function of the whole command lines that include the input file's path, its content, and the path of the outputs, which are most relevant to the context of output path mapping. And so in these two black boxes you see here, these are the example of the paths that a command line of an action could contains. And on the right side is a action that cross-compiled to Linux. But because you see in the CPU informations and the compilation mode highlighted in red and oranges here are different from the two action, and even though they result in the same output, the action on the right side that cross-compile to Linux does not benefit from the previous work that was done by the first actions. And to help with this problem, we introduce path mapping. So I'm gonna go back and walk you guys through where we integrate path mapping into our current flows. So when a user sends a build command to build a target, Bazel breaks that into multiple actions. And then for each of these actions corresponding spawn object, which is a subprocess that will be invoked by the remote executor. Oh, sorry. And so if the action declares itself to use path mapping, then a path mapper will be created with a spawn. And the responsibility of the path mapper will then remove the information that was highlighted in red and oranges here out from the command line, simplifying it to look like this in the black box. And because these paths are rewritten on the command line, the remote executor then responsibility tends to stage the input files at the paths that were rewritten. A few things that I want to note here that you see the path here on the command line in this example are in this perspective of remote executors. So after the remote executor returns its output, Bazel then mapped this into using the same the full path name and so that it could continue to exist with the rest of the build outputs. So this means that when this feature is on and user do a build and after that you examine the Bazel out, you still see the exact same path that has the CPU or compilation mode information that we saw before. And the second point is path mapping only merges paths that are differed by paths, but not by contents. So this is considered safe, unlike cache key scrapping that Tiago will get into in the later sections. And the third point is not all actions are qualified for path mapping. Therefore, currently, we maintaining a list of action mnemonics that we apply path mapping for, mostly just at Java and Android rules. So in this slide are the example of actual impacts on real projects that are in Google 3. So on the left side is the YouTube Android app, and on the right side, it's a Play Store Android app. And so the nature of this experiment is very controlled so that I only see the benefit of output path mapping alone and not together with other caching system. So you see for the YouTube one, it consists 15% of Java library and Android library rules. And we see an increase in number of action cache and a 25 reductions in both time. And then for the Play Store, we see 11% of Java and Android rules with nearly 40% reduction in both time for subsequent builds. So right now I'm gonna pass over to Fabian, our collaborator, to talk about state of thing in Bazel. Thank you.
Chiara. Thank you. Okay. Hi, everyone. I'm Fabian. I'm the non-Googler working on this project, and it's one of the interesting examples of, well, very interesting and challenging rabbit holes that you can get yourself into. So 2.5 years ago by now, some people at my company complained that they were recompiling Proto-C 16 times. I mean, we're not Google, so the scale is not that large, but 16 is a lot. So I looked into it, and I saw that this was caused by rules Go using transitions that leak into output paths. And then fast forward, I'm here talking about a way to sort of solve that, hopefully. And in line with Benjamin's talk, we'll now go from the theoretic section that Ara talked about to how you can actually use path mapping today in Bazel. And the good news is that the latest RC, so RC2 and RC1 of Bazel 7 are actually pretty good. And you can start using most of this, not everything, but most of this today. There's one incremental flag that you need, incremental output paths, and if you set that to strip, that will enable path mapping globally, which then allows action to opt into it, because we can't opt every action into it. Not every action may be compatible with it. And then, as I mentioned, you need some kind of cache. So you need to use remote cache or disk cache to actually make use of this feature, otherwise it doesn't give you much. And you need to use the supported execution strategy, because we need to do some kind of dynamic remapping when we stage something for execution. This needs to be something, essentially think of symlinks. So we need something that does symlinks. So that excludes any kind of unsandboxed or local execution. So on Windows, for example, you can only use this with remote execution, but that should work on all platforms. And unfortunately, there are some multiplex workflow issues that I'll get to. And as I also mentioned, the most prominent example of well, platform-independent build results is Java and everything, like, think of everything JVM. So far, we've focused on Java, and path mapping there works for essentially everything. So it applies to the full compilation actions. It also applies to this Bazel concept of header compilation that's sort of supposed to flatten your build graph. And it also applies to some bootstrapping actions that are a bit less relevant. And it should just work. So if you use the flags from the previous slide, it should just work, with one caveat. So remote execution just works. Unfortunately, the default compilation mode for Java is a multiplex unsandboxed worker. That's a mouthful, but relevant bit, it's unsandboxed, so it doesn't work. We'll improve that. So far, you need to pass this no incremental worker multiplex. Here's an end-to-end example. So if you want to try this out on Bazel itself, you can just use all these flags, and then you build in the default compilation mode, which is fast build. And if you do that, and then later on, you switch to compilation mode opt, which is reflected in the output path, you will get cache hits for essentially all Java actions. So that's one way to give it a try quickly. And you can see, if you look at the command lines that you run, that this is essentially just because we dropped this config part out of the flags, out of the path. And now the important question for rules also is, how can I now apply this to my rule set? For example, rules Go would want to use it, and probably rules Kotlin as well. There are two ways. You can do this in Starlog. You can provide a well-known execution requirement, support path mapping to show that your action is compatible. Or you can do it from the CLI. If you just want to try this out quick and dirty, you can enable it for a certain action based on mnemonic. And this is incrementally correct if you toggle this. So for example, if your action depends on debug symbols that reference paths in debug mode, you can selectively not pass in this execution requirement in that case. I'll quickly go over the slide. There's essentially one rule that tells you whether your action is compatible with path mapping. Good thing is, if you follow these rules, Evo will like you, because memory consumption, the memory gnomes will be very happy. This aligns pretty well. If you use structured command lines, you avoid eagerly creating command line strings, that's pretty well aligned with making your action compatible with path mapping. So there are some don'ts and do's. General rule is everything that has full paths in it that mention this configuration prefix, you should only let the args object for structured command lines construct lazily, and don't do it in your rule implementation. Yeah, these are the detailed things. Some things will only work in the full Bazel 7 release, not yet in the latest release candidate. So let me go over the future plans. Java is pretty done. There are some corner cases that we need to look into, but I hope that those will be addressed for the full Bazel 7 release. And then the next step, I mean, I'm also a maintainer of Rules Go, so Rules Go, it's transitions. Well, we feel sort of responsible for also applying it there. And then I will also look into and talk to the Rules Kotlin maintainers to maybe have a full Starlog end-to-end example of JVM compilation using this feature. There's one caveat. So there are some location expansions that are problematic because they're not structured. They're just strings. That's something that we'll try to approach and tackle a bit more comprehensively. Yeah, and then there's also an application to Bazel mod where this can also reduce rebuild churn caused by updating dependencies. Yeah, and your feedback is very welcome. Please just give it a try. And I'll hand over to Thiago.
All right. So I'm going to talk about another feature that we're introducing in Bazel 7 to facilitate cross-platform builds. And we're calling this feature cache key scrubbing. So let's recall this scenario from earlier, where we have a single project built on 2 different platforms. On the left, we have a developer building the project on its macOS laptop. And on the right, we have a CI pipeline building it on a Linux machine. And notice that only the execution platform differs between the 2 builds, because the compilation output is a jar file, which is platform agnostic. However, and Greg has already explained this, because the Java compiler is a native executable, it has a different path and also different content on each platform. And therefore, if you do a build on Linux, populate a cache, the cache will not be hit by the macOS build that you go after, or vice versa. So let's recall again how we store action results in a remote Redis cache. We have this thing called the action cache. It's a key value store of action results. And the key to these cache entries is something we call the action digest. And this is just a hash of a protocol buffer message similar to the one on this slide. And for simplicity, I'll just call it the cache key going forward. Note that the key contains every detail that could possibly affect the action execution. So it's the input paths, the digest of the input paths, and the command line arguments. And again, this is a very simplified example, but in this simplified example, you have an action that compiles a Java source file into a jar using the platform-dependent Java compiler, and the bits in red are sort of the platform-sensitive parts of the cache key. So scrubbing is a process by which the platform-dependent details are erased from the cache key, so you can have a uniform cache key across execution platforms. And in this example, we are applying 2 transformations. First, the platform-dependent Java C input is omitted from the key entirely. And second, the command line arguments are rewritten into a sort of platform-agnostic version. And if we do this, then we can use the scrub key when reading from or writing into the cache. And so this way you can run a Linux build, populate the cache, and then later run the quote-unquote same build on macOS, and you will be able to hit the cache, hopefully, because they're both using the same scrub key. There's one additional problem. Sooner or later, you're going to have to upgrade the Java compiler to a later, possibly incompatible version. And this version might not be able to share the previously cached results produced by the previous version of the Java compiler. And so to make it possible to disambiguate between the cache entries for these 2 versions, the user-supplied salt may be included in the key. And this is just like a completely opaque string. It's JDK 18 in this example. And this is completely controlled by the user. We're not going to interpret it because we want to provide maximum flexibility around cache invalidation. I'll just mention very quickly, this is really only about storing and retrieving entries from the disk or remote cache. It does not affect Bazel's internal model of correctness. It does not affect how the action is invoked, because the recent command line would not work at all. And so it has a practical consequence, which is that you can make local modifications. It will still trigger a rebuild, even though you might hit the cache anyway. And toggling the scrubbing on or off will not, by itself, invalidate the local results you already have. How do you set up scrubbing? You pass in a configuration file, which is a protocol buffer in text format, and we're going to take a quick look at what that looks like. So here's what it looks like. Configuration is a list of rules. A rule is a transformation and the set of actions that it applies to. The matcher describes which actions are affected by the rule. Actions can be matched by mnemonic or label. Both can be given as a regular expression. In this example, we match all Java compilation actions for targets in the main repository. And the transform describes how the cache key should be scrubbed. List of inputs to be omitted, list of string replacements to apply to the arguments. And then finally, the user-defined cache salt. I'll just mention very quickly, because I'm running out of time, apart from the configuration file, there's 2 flags that you can use to make scrubbing a lot more effective. First, you should consider defining a custom host platform and using its name as the configuration prefix. This is the platform in output there flag that was mentioned earlier in the previous talk. And second, you should normalize your environment variables, because as it stands, you cannot scrub them. This is something that you have to do through some other means. This is a very experimental and low-level feature, so it comes with a couple of caveats. First and foremost, scrubbing improves performance at the cost of correctness. So scrubbing too little will prevent the cache from being shared, which is bad. But scrubbing too much might cause cache entries to be incorrectly shared, which is also bad. As it stands, basically, the user is responsible for ensuring that the configuration is correct. And coming up with that configuration is sort of a trial and error process. It might also have to be, whatever configuration you come up with might have to be adjusted on a toolchain upgrade. And for more information on how to set it up, you can look at the flag documentation and the protocol buffer format, which is in the Bazel repository. So while we believe that this current implementation of cache key scrubbing successfully addresses user needs to some extent, I'm also going to acknowledge that user experience right now is far from perfect. This is just a starting point to this feature. I'll briefly mention some aspects in which this could be improved. First, we're currently lacking good tools to pinpoint the root cause of cache misses, which is important because of that trial and error process that you would have to go through to write the configuration successfully. And this is something that we're actually planning to address in the coming months by rethinking the way we do the execution log. Next, we envision that maybe in the future, the toolchains themselves might be able to provide configuration rules so that the users don't have to write them themselves. Finally, scrubbing is currently not compatible with remote execution. This is not, in principle, impossible. It's just that we would have to modify the protocol, and this is sort of, the conversation is wider than Bazel here. It has to involve the various implementations. And I think that's it. I'm not sure that we have time for questions, but thank you.
Thank you, everyone.